Hi, Ron. So today I'm going to be talking about a topic very close to my heart. I've worked on this topic for maybe a year or two. And, after working on something for a year or two and not 5 years, you're still very passionate about it. You think you can solve problems relevant in the field. You're very happy and excited about it. So this is kind of, it's where I am with the turbulent dynamo. There's a couple of things just before I get started. I have a plan here. And I mean, this is the first time I'm giving this talk. So as I went through it just before, I decided to swap these two initial parts of the plan. So I'm going to start with just setting the scene for the small scale dynamo. And I'm going to use these terms, SSD. This is just small scale dynamo. And dynamo, of course, we'll talk about it in a lot of detail, is really just the process in which you grow a magnetic field from various types of mechanisms. So I'm probably going to use this SSD just because it's nice and short. But here I also mean turbulent dynamo. So this is a coupling between a turbulent plasma and a magnetic field, making it grow, which is what we'll be particularly focusing on today. And also, some people call this a fluctuation dynamo. So pretty much these are all very much the same kind of term, and you can see fluctuations are associated with turbulence. Turbulence has a particular structure with fluctuations, but still same sense. So this is where I'm going to start setting the scene for the small scale dynamo, and to actually build up an idea of how this works, we're going to have to talk about turbulence. We're going to be starting in the most vanilla case, and probably ending in the most vanilla case as well. We talk about Kolmogorov turbulence, which you've probably all seen before if you're taking any kind of chaos class and chaos, nonlinear dynamics, etc., etc., etc. So after we get into, after we finish our kind of venture into turbulence, then we'll talk about turbulent dynamos in astrophysical processes, and I'll give you a whole bunch of slides about dynamos in various mediums, and then we'll go into an overview of the different stages of the dynamo. So that's the rough plan. Okay, so if we're talking about turbulence, we of course have to talk about, and fluid turbulence in particular, we have to talk about the momentum equation. So momentum equation, I'm going to be writing it down in its conservative form. So that is the derivative of the momentum is going to be equal to a whole bunch of conserved fluxes. And I'm going to be writing it down without any dimensions as well. So here's the vanilla momentum equation that you probably have seen many times if you studied any kind of fluid dynamics. And what you're seeing here is it written out in terms of conservative fluxes. As I said, this is essentially the maximum stress. So this is the coupling of the magnetic field with the momentum equation, which just looks like two terms. Here, this is just the tensor product. And you have, of course, the magnetic tension, and you have the isotropic magnetic pressure. So this is all contained in the Maxwell stress tensor. Now, also note, and we'll get back to this later, that this Maxwell stress tensor is actually symmetric. And this is an important component of the magnetic field when you talk about fluids, because the nature of the symmetries and the tensors will tell you how it couples to essentially the fluctuations later on. What else do I want to say? Well, I mean, if you just take the divergence of the tensor, this is the score that people get an idea of you just of course get this, and this is just a regular line. So nothing crazy. I've just rewritten the Maxwell stress in terms particularly of the stress from the tension and the stress from the isotropic pressure. Okay, what's our S? So we have the quadratic nonlinearity that we'll talk about. We have the Maxwell stress. We just have the isotropic thermal pressure. We have some kind of source function, which essentially can be the source of our turbulence or something like this. And then we have this term, which of course is the resistivity or the viscosity. Now, viscosity, you can prescribe all different kinds of viscosity. Throughout these lectures, I'll just be using the simplest prescription of viscosity. By the way, this is just the identity tensor. So here's my viscosity. Essentially, it is just the rate of shear tensor or the rate of strain tensor. And you can see by adding this extra term as well, I've made this tensor traceless. So the trace for my rate of strain is going to be 0. So why is that important? Well, of course, this is a tensor acting on our fluid element. And essentially what I'm saying is that this viscosity operator cannot actually change the volume, right, of the fluid element. That's what really this means with the trace of 0. Because you can think of a fluid element. Essentially, the tensors are going to tell you about the forces acting on that fluid element. And if the trace is 0, it's then sum over all of the forces acting on that fluid element, and they add up to 0. So you cannot expand or dilate that fluid element. Right? That's the sum is always 0. What? Yeah.
The definition of S, the 1/2.
Oops. Yeah. Good point. That should be the trend. So this is our momentum equation. It's just the force balance F equals NA for our fluid element. Now there's another important equation for doing dynamic, and that is, of course, the induction equation. I was going to plan to put these over here so I could point back to them, but I just stopped doing that. Induction. I talked a lot about the induction equation yesterday. Oh, sorry, last week. But also yesterday too, probably. And again, I run it down in dimensions. The induction equation is much more boring than the momentum equation. There's really just 2 terms here. There's the induction term, which is why we call it the induction equation. And then there's the resistive term. So this is the non-ideal induction equation, where you actually have some resistivity coming in the form of a Laplacian operator acting upon B. So this is some kind of local resistivity. What else did I want to say about that? Well, you can also rewrite this equation if you want to, in terms of minus where J is our current density. And this, of course, is something that I would really love. This is, of course, just the non-ideal electric field. So you can see that the induction equation just has the, it just really is the equation, the evolution equation for the curl of the electric field, as you would expect from open source. But this is not a very nice way of running for dynamo problems in particular, and we prefer this way. So, and this, you can see, this is just an advection term, right? This is just the advection of the magnetic field. So this whole term is just a Lagrangian derivative. And so you're just moving along with the fluid element and tracking the magnetic field as you move along. Now this term here, so the B dot Brad U term is actually the dynamo term. So the way that the magnetic field couples to the velocity field is in terms of the velocity gradient tensor. So this is the small scale dynamo term. And then of course this is just the vanilla resistivity again. Now, let's actually go to turbulence itself. We have now the key equations of evolution for a fluid in the momentum and the induction. Particularly for turbulence, what is important hydrodynamically is the quadratic nonlinearity of this term. So this is quadratic in the velocity, in that it scales like u squared over L. And this is nasty. This is a nonlinear term in our Navier-Stokes equation. Now there's a term that counteracts the nonlinearity, which is of course mu, the diffusion term. This limit. This limit. Okay, so there's essentially this competition in the momentum equation in terms of terms that involve the velocity between the quadratic nonlinearity and the diffusion. And we can write this down in terms of the dimensionless number. I've already written it here. And we call this, of course, the Reynolds number. Now you can already see when the Reynolds number is very, very large, in the case where the Reynolds number is very, very large, the quadratic nonlinearity dominates, right? So the Navier-Stokes equations become really, really strongly nonlinear. And if it's very, very low, in the case where it's very, very low, the diffusion dominates, and this thing fundamentally becomes a diffusion.
Can I just quickly ask, so usually the Reynolds number is written in terms of large scales, and here you've written in terms of something local. Are we supposed to think of this as an average of the flow? Or?
Yeah, so this, you can think of an average over the flow, but you can also compute the Reynolds number as a function of L, of course, local quantity L. But when you do the dimensional analysis, exactly as you said, you just get this coming, right? This is the order of magnitude of the Reynolds number on the large scales. This is what the dimensional analysis gives you. But really, the definition in terms of the fluid dynamics is this, right? This is the sim, and this is the actual definition, in my opinion.
Check with Reynolds.
Yes.
We're probably not going to make your actual definition of Reynolds not be a constant throughout the entire.
No, it's not. The Reynolds number changes the function of scale, for one. So it fluctuates, right? It has a correlation function.
I guess my question is in the initial momentum transfer.
So, I mean, this Reynolds number that I've defined here is for the local, this is for every cell. Then you can imagine the case where you force squaring this equation to larger and larger, you define a Reynolds number. I mean, it's not your focus. So accretion disks. I'm thinking thin, I'm thinking fold. RE is approximately 10 to the 12. Fold ISM, just to give you some numbers here. And I'm thinking molecular cloud and CITA. RE is around 10. So that is if you are writing down the fluid approximation for both of these types of plasmas, this term is going to be dominating the equations of motion, right? Reynolds number is huge. I mean, as Chris pointed out, essentially the Reynolds number scales linearly with length scale. So just as you go to large length scales in the universe, you can reach very, very large Reynolds numbers. You don't even have to change the velocity, it's just linear in length scale. But of course, also the dissipation, the viscosity here is also very small compared to UL in general. Viscosity happens on small scales, and our UL can, respond to L. So when the Reynolds number is very, very high, we venture into the realm of turbulence. Okay. Now, how should we understand turbulence? Well, you've probably seen these classical fluid dynamics experiments where you either increase U or you increase L for a fixed viscosity, and what you see is all this swirl, right? See all these nonlinear instabilities appearing in your fluid. And essentially each one of these swirls, the length L, is called L naught, that biggest swirl. Have smaller swirls, as the L1, even smaller swirls, L2, L3, etc., etc. So each one of these has some kind of length scale. And of course, there is a time scale associated with each one of these swirls, this L over UL. So that is the velocity on that length scale. Yeah. And let's just pretend the case where the energy flux from this swirl is transferred to smaller swirls, neighboring swirls of kind of neighboring length scales with a constant energy flux. And then the same thing happens here. So the energy flux goes into smaller and smaller with the same energy flux. So there's a constant energy flux moving from large length scales down to smaller and smaller. So the energy flux. This is going to be essentially units mass L squared over E squared. You just did a dimensional analysis for what your energy flux per mass should be. Okay. And so we can easily work out is that the energy flux has to essentially look like L squared over T cubed, which also looks like U3 over L. Okay. So I'm trying to write these down, this energy flux down in terms of the properties of my swirls. Okay. So where do we go from here? Well, I want to know what the velocity and the kinetic energy of these swirls are for the case where there is a constant energy flux between all scales. Does this make sense? I'm saying words that make sense. Just double check. Chris, give me a thumbs up. So that's very simple. We already have a relationship between our velocity and our length scale from the assumption of constant energy flux between neighboring scales. And of course, this is just U. Okay. This is from our gross. So, I mean, how should I think about this U, right? Yes.
So, James, I've seen fluid table in this like total argument 100 times. Can you make this more rigorous with like Fourier, spectra, and stuff? Always.
So we can't go from there to there, if that's what you mean. That is the turbulence problem, I would say, or one of the key problems with turbulence. There are a few amount of exact relations in turbulence theory. And one of them is really, the only well-known one I know is associated with the third order structure functions, which is about how essentially the higher order statistics of these swirls, essentially a balance of the higher order statistics of the swirls. And you can get that from the Navier-Stokes equation. But can't do much better than this. I mean, you know, we can talk about the kinetic energy, of course. Wow, more tilde, you know, our tilde arguments are strong here. We can talk about the Fourier transform. Why not? Of course, we're going to put this in K space. So K sim 1 over L. 1 over L. So the Fourier transform is just, of course, another way of measuring our structure, our fluctuations of the function scale. And of course, if we just plug this in, we get u squared of K, all this. And we want the energy density. So per unit K, and we just get the phase from the result. Okay. So,
That's a really important question. So,
Yeah.
When we drew at the top right corner, smaller spirals.
Yeah.
Seem to be spatially distinct from large spirals. And actually, like the large spiral has a small spiral on top of it, and then has a small spiral on top of that. And so all these-
well, you have to consider the case that Kolmogorov was thinking in terms of. So really, the organization of the chemical eddies were closed loops of velocity. And I don't really know what, so you're saying, is there a small spiral in here?
Yeah, so let's say there's both motion and it's like large spiral over large length here, and then inside, like mostly fluid line.
Yeah, I mean, there is. I mean, this eddy has a profile of some kind, but the eddy is really we do see eddies, but I mean, and eddies, eddies are vortices, and vortices have profiles, and you can measure how the shear changes across the eddy like this. But I think this is just a nice way of visualizing. You have multiple scale eddies interacting, transferring energy from one scale to another scale, et cetera, et cetera. But I see what you mean. So you're trying to say that a single eddy will have a whole Fourier spectrum itself. That's true. That's true. But the way that I want you to think about it is that each one of these eddies has a length scale which has a particular K mode associated with it, and let's draw that picture now. So let's put the energy here, or something sim the energy. And what does that spectrum tell us? Okay. Okay, the minus 5 goes. So let's say there's some length scale of the largest eddy. 1 over L naught. We haven't talked about what's down here yet, but we'll get there. And it seems like if we follow Kolmogorov's arguments, we're just going to get this. Okay, then minus 5/3. Yeah. And the way to think about this too is the energy flux from scale to scale here in this kind of fashion is constant and moving this way. I mean, actually, the directionality is not really in the arguments, but let's pretend that's a direct cascade, moving energy from the lower scales, our outer scale of the terminals, we'll call this, just fall on small scale until something happens. Now let's talk about that something. Okay, well, pretty much just from this, we can actually do a lot of work here. A lot of interesting work. Just take it this way. I had these grand plans of having like this really organized blackboard. Yeah, just all over the place. There goes all the astrophysics. All right, so that should. So we're going to keep going back to that picture. And what I want to do is work out where this cascade truncates based on the idea around the Reynolds number that we have UL over nu, that there is some length scale L, right? And we know now that this is a function of L as well, UL, L. So we know that, of course, from this argument over here, we have just L 1/3 plus 1 over nu. So our Reynolds number changes the function of length scale, my point. And you can imagine you walk down the cascade, walking down the cascade until you get to around Reynolds number REL, something like 1, and the diffusion starts dominating. So you kill off all the nonlinearities that we were just talking about, the quadratic Reynolds stress. Okay. So we want to now determine a viscous length scale. And of course, so this is my viscosity coefficient. It's a diffusion coefficient. You know, it has units of length squared per time. It's a diffusion. So let's write that out. We're going to stay with the tilde theme there. I mean, you're not going to get much more out of it than the tildes, unfortunately. Until we get a dynamo. Dynamo, we could write equal signs. But I don't know if we're going to make it. I'm looking at the time. Anyway, let's keep going. So we have a velocity on the viscous length scale. We have viscous length scale. So this is going to be equal to our diffusion coefficient, of course, in the tilde sense. Essentially, you can write that down in terms of just length scales and our constant rate flux, our constant energy flux, in terms of this. I'm going to go through the algebra and do it more. But I didn't have any set on my notes if anyone was interested in going through these. I've got the full derivations here. So you can write down nu in terms of just the fundamental quantities, and then you can just, of course, convert this to get out L nu, dissipation length scale, and this is just going to be 3/4 epsilon dot times. Okay. Now, the extent of the cascade is going to be wherever I place L nu down here. And there's something to do with, you know, going from the outer scale to 1 over the, you know, the extent of the cascade, the extent of where the modes are nonlinear, interacting with each other and forming this theta minus 5/3. So we want to really compute this quantity, L nu over L naught, which is the ratio. And you can do a little bit of work here to show that it's going to be like this, L naught over nu to the power of 3/4. Not very hard to show this at all, which of course is just the Reynolds number to the power of 2. This is cool. This is cool. This tells us that the extent, the size of this range is Reynolds number to the power of 3/4. So that means it is the size of the Reynolds number in all these different astrophysical flows that tell us the size scale of the actual range of nonlinear, of where that quadratic nonlinear dominates in the fluid equation. Really cool, I think, right? Now we can play the same games for the time scales. Where do I want to go? We can play the same game with the time scales and also the velocity scales. So T naught over T nu, scales like RE to the 1/2. This is going to be important for us later. And U naught, scales like RE to the 1/2. So all of these things tell us exactly all the information that we need about the cascade. They're telling us that the slowest eddies are up here. The fastest moving eddies are down here at the viscous scale. So this is where the characteristic time scale of the eddies is the fastest. And of course, it's also telling us the highest velocities are up here. I mean, this is just obvious. And the lowest velocities are down here. But there is a lot we can learn just through tilde arguments and the assumption of constant energy flux. So you should think about these big eddies on these scales, these big eddies on these scales, transporting energy down to smaller and smaller scales, and the turnover rate is becoming faster and faster until it's maximized here. And then you have diffusion. The nonlinearities have been dissolved out of the equation. I think that's all I want to say about hydrodynamic turbulence. Do we want to
Summarize the role of Kelvin's theorem.
Kelvin's theorem to do with vortex tubes?
In that stage. Yes, why do you doing planar heavies? That's one way. That is planar heavies as opposed to higher dimension structures.
Why am I considering planar eddies? Because I want to get through this in around 15 minutes. And I wanted to have the simplest case possible so we can move on to that. I mean, this is the classical K41. That's what I wanted to do.
Can I just follow up on the black ones? Okay,
Also the blackboards.
so have you gone into your entropy arguments yet?
No.
Well,
That's a very big
the
question.
thing that is quite amazing is
Yeah.
that as a function of scale, the Kolmogorov spectrum
Yeah.
gives you entropy as 3/2 log, where R is the scale, and that's K inverse. And that's not unlike what happens, believe it or not, in clusters and things like that. It's a slightly different power law. And then, so that's question one. Question two is if you turned off the eddy aspect, that is to say the V curve, the perpendicular, the axial component of the velocity, would you still be able to get a cascade if it was effectively potential? Or
These are all V-perm. These are all V-perm.
I know that.
Yeah. So is there a compressor mode to cascade?
That, yes, exactly.
Well, Dick, I mean, parts of my scale is it's all.
Well, no, that's all being perfect.
And goes the other way.
I don't see why that's got anything to do with it. But maybe. The main point is that if you look at the early universe and what comes out of it, there's a velocity dispersion which also goes with
Yes.
some power, more or less.
We're working under this assumption where there are no longitudinal modes.
Yeah, yeah, okay, so it's, you're thinking that.
Just to the point of the simplest possible model turbulence that we can put on the blackboard.
So the Kolmogorov turbulence in higher spatial.
Yes, they have, actually.
Because I would think that coherent structures become less and less important. As you go to higher and higher dimensions. Like the Kolmogorov thing.
Yeah,
I mean, the indices, of course, will be modified.
you know what is really cool, actually, now that I think about it? People have considered Kolmogorov turbulence in fractal spaces where they change the fractal dimension of the space between 2 and 3, and they see a sign flip in the energy flux as you move closer and closer to 2, of course, which is so cool, right? So you can smoothly change the dimension, the underlying manifold, and you see the flux slowly go back up the cascade. Because, by the way, this is a 3-dimensional, at least eddies should be 3-dimensional. But in 2D turbulence, the energy flux actually goes this way. You have an inverse cascade. And I mean, you can think about that as kind of little vortexes merging into larger and larger vortexes and shooting energy back up.
This is why I was asking about deltas.
Yeah.
Because I think this is an under discussed aspect of it.
So this is a direct cascade when we go this way, and then this is the inverse cascade. And in MEG turbulence, there are both inverse and direct cascades happening at the same time. Seemingly all the time.
So the executive summary though is that in higher dimensions beyond 2, you have a downward cascade as Kolmogorov predicts. With the same power law.
Well, I mean, you are interested in energy densities. So
you use the same argument.
yeah, exactly. So your density keeps changing, and you actually keep reducing down to the negative 5.
And is the inertial range, which is I think the point, is the inertial range increased if you're in higher dimension?
I am not sure.
Like, it would-
Okay,
somebody would know.
so now I want to quickly. So now we know about turbulence and fluctuations, and this is our background medium. This is the stage in which the turbulent dynamo has to live on, essentially. So you can't think about it as all this kind of laminar flow, this laminar universe. It's a fluctuating universe. and you're adding a seed magnetic field, let's say we're adding a seed magnetic field to this picture, it has its own power spectrum, it looks like this. You can say just a single band, A naught. And we're going to ask the question, what does this spectrum do and evolve as it's coupled to the turbulence? It's going to go through a number of stages, a number of different phases as it goes through different types of growth. But I think first what I want to show you is just some examples of this in various plasmas. And all of these plasmas have, or all these experiments rather. I mean, I could show you lab experiments as well. Really, these types of dynamos are very, very ubiquitous, which makes them very exciting. I have to do that. So all of these experiments, this is a cosmological simulation with Milky Way. They've essentially selected Milky Way type galaxies using the record. And what they find is when they track these galaxies and the galactic magnetic field through time, is that they find that the magnetic field undergoes this really fast exponential growth stage. So there's some kind of very fast dynamo process happening. They teeter off. So this is log linear. So these curves actually probably are linear in linear space. So the growth rate teeters off to some kind of secular growth, and then it's saturated. Okay. So this is a hallmark signature of a small scale turbulent dynamo. And you can already see that there are multiple phases to the dynamo. There are some exponential growth phases, secular growth phases, and then saturation. So this is entire galaxy scale.
With feedback.
With feedback. This is a merging neutron star. So there's neutron star here, neutron star here. Exciting at Kelvin, Helmholtz instability as they merge. So they're orbiting each other, exciting the shear layer right here, Kelvin, Helmholtz instability. They're computing the magnetic field in the crust. And then also in the core region. You see again, very, very fast. So this is the magnetic field energy density. Very, very fast exponential phase. Something of a pause, and then another exponential phase, and then a secular growth phase again. So again, there's this kind of multi-phase nature to this type of dynamo.
You think that's a uniform phase? It looks to me like it's a bit of an overshoot, and then it has to come back.
This one is very interesting. Associated, at least from my experiments with this kind of dynamo, associated with 3D instability coming into play. Now I'm just going to a broad range of simulations now. So this is molecular clouds and first generation stars by Kirsch. This is intracluster medium studies by Ulrich. This is Franco Vasa's work on cosmic filaments, all showing the same kind of signatures, at least in their volume integral statistics, right? So these are energy densities across the volume. You see an exponential growth stage, you see a saturation, exponential growth stage, saturation, exponential growth stage, saturation, and of course this rounding off, like I said, in log linear is actually a linear secular growth stage. So I would argue that whatever is causing this magnetic field growth, which I think is a small scale or a turbulent dynamo process, is very ubiquitous across different fluid plasmas, but not only fluid plasmas. You can do weakly collisional Radinsky MHD in Princeton. You can do completely collisionless plasmas from one of my colleagues at ANU, and you find the same thing again. Collisionless plasmas are actually you have to integrate these dynamos for a while, and this is a very expensive experiment, so they've only been able to resolve the first stage, which is that exponential growth stage, but this is a purely collisionless plasma. And then again, you see the exponential, you see the turnover. And this is with Brzezinski MHD, where you have essentially a different kind of viscosity stress.
In this context, collisionless means that it's all mediated by.
So, I mean, it's a Pixie motion, hybrid Pixie motion. So you have essentially particles exactly like that.
So that's, I mean, it's semantics, but it's not. Because it's mediated to the field.
Well, it's a completely different set of dynamical equations.
All interaction.
Yeah, but it's a different set of dynamical equations.
There's no Coulomb.
Yes.
That's the. No. So lots of equation rather than.
Like a different scale.
Completely different set of like. Yeah, it is surprising, I'd say, that there is such a universality. I mean, these are very different things. This one is a very nice study by Martin Alfres. He's essentially one of the only people that computes power spectrum for cosmological simulations. And what you're seeing here is a set of merging galaxies. He's computing the power spectrum of the magnetic field as they merge. And all of these, so remember back to our power spectrum, these are the large length scales, these are the small length scales, right? Low K, high K. You see all these high K magnetic modes being excited, and it gets the same kind of exponential growth again. So I think I would argue that the turbulent dynamo is very, very ubiquitous across all these plasmas because it relies on such very simple and universal features of our universe. One is turbulence, high Reynolds numbers, and the other is the presence of a C magnetic field. That's all you need. Those are two ingredients you need for this mechanism to grow a magnetic field by orders of magnitude within a few electron times. So let's actually talk about the dynamo now. In the last 15 minutes or so, where a majority of the content of this lecture is. So how do I want to summarize this? So as I said, now we're thinking about adding a seed magnetic field to this already turbulent plasma. I'm asking the question what the seed magnetic field is going to do. Well, there's going to be 4 phases to this dynamo process. And these have been identified numerically, but you know, we can write down analytical theories for the first 3, and the last one is very tricky. Hasn't been solved yet. Convincingly. So the first phase is the diffusion free. Maybe just draw power spectrum. Maybe that's not. It's the diffusion free phase. This is the diffusion. Kinematic stage. This is the secular growth stage, which we unfortunately saw the nonlinear stage, even though the growth is linear. And then this is the saturation. So let's consider a simple case. Now I'm just going to throw my notes away because it's just useless. I have to draw a big power spectrum. So this is K. Here's our turbulent cascade. You know, this is our 1 over the outer scale of the turbulence. This is 1 over the inner scale of the turbulence, i.e. the viscous scale. And let's pretend we start a magnetic field over here. But actually, I showed, well, actually, this was in my 2023 work, that it doesn't matter. Where you start this magnetic field, it doesn't matter what kind of field structure the initial field has, the turbulent dynamo does not care about the C field at all. So what is this?
So for instance, silicity doesn't matter.
Helicity doesn't matter. I should have been more specific. If the field has helicity or not, it doesn't matter. Anyway, so what you're going to find very, very quickly is that this the C field is going to evolve into kind of a blob that moves like this all the way to some very small scale. This is large PM plasmids. By large PM, we mean that the ratio between the resistivity and the ratio between the viscosity operator, that's our new. This is my viscosity operator. A PM much larger than 1. I mean that the RE, so, oh, sorry, the RM over the RE. In other words, I mean that the resistivity, so the resistivity is very small compared to the viscosity. Right?
So the field can go to scales.
Exactly, exactly. So you can also write this down as mu over eta. So in other words, yes, I'm thinking PM much larger than 1 plasmas. And B, this is not just because I like PM larger than 1 plasmas, ISM cold. PM scales like T before, by the way. 10 to the 4, ISM hot is 10 to the 20. For PM, this is all PM. I've also got the PM for galaxy clusters here. Is 10 to 29. Yeah. Obviously, this picture doesn't hold everywhere because you can imagine if the PM is very small, the resistor scale is in here, and you can't travel this long distance before you start running into resistivity.
So the thermal scale, this scale, is relatively short distance. And you're saying that you go to much higher K,
Yep,
What's
much
the
higher
time?
K. If PM is
so you don't have any vortices.
no,
Oh, damn.
no vorticity there. No vorticity. And we can work out how far this travels, because essentially the idea is that there's a peak of the magnetic spectrum and it's shifting further and further to high K. How far does it go? Well, let's do some tilde calculations. And this is actually very fun. Oh my goodness, I'm missing so much stuff. Oh, so let's work out where this resistivity scale is. And what we can do is we can balance the stretching on this scale. So this scale, like I said, it has a turnover time associated with it. It's very, very fast. It's the fastest turnover time in the fast system. So this scale, at the viscous scale, is very, very efficient at putting energy into the magnetic field. In fact, it is, and we found this numerically, that this is the dynamo engine. The viscous scale is the small scale dynamo engine, which is unbelievable.
Do you have an idea of where it stops?
Yes?
Okay, so.
Yes. So there's a rate, a stretching rate associated with this scale. So that's just it fundamentally is just 1 over the turnover time, but here we're thinking about that the gradients on these scales. Remember, the dynamo is the coupling between the gradients of the magnetic field. This is where they're evolving the fastest, so this is where we get the strongest coupling. We can actually show this numerically, that is true. And we're going to balance this with the numerical resistivity. And this is just essentially the resistive rate of the magnetic field for a given resistivity coefficient and the resistive length scale. And what you can show is this gives you L eta, L mu, PM to the 1/2. So that is, the magnetic field will travel to higher and higher K modes all the way until it gets to the resistive scale. And this distance from here to here is PM 1/2.
That maybe PM to the -1. Ratio. So it's a smaller one.
Let me just think about this for 1 second. You're totally right. Actually, this should be the other way around. Yeah. That's right.
Reconnection taken into account in all this.
We don't need to care about reconnection at all. The magnetic field is very weak, extremely weak. It is essentially passively affected by the velocity of the field. You know, the magnetic field is 10 orders of magnitude weaker than the velocity.
Is that an assumption? Is that by
I mean, that's just
definition?
for whatever you want to put in for the C field, right? But I mean,
But is it getting,
it's
Less
getting
weak-
stronger.
yeah.
It's getting stronger. A lot of, so, you know, we can actually work out the spectrum. We have an analytical model for this magnetic spectrum. And you can work out that every single mode here, every single mode is growing exponentially. The gamma T. The amount of modes that it's covering in time also grows exponentially. So like the mode, like the sigma of the spectrum, essentially. This is a magnetic spectrum. Is also growing exponentially gamma T. So it expands, covering exponentially more modes all the way down to the resistive scale. And every single one of those modes is growing exponentially. And the peak scale, this peak scale Kp, is also growing exponentially. And these are not the same growth rates.
but is it an assumption that the magnetic field is so weak that it's not dynamically important before it gets to the scale?
It's not dynamically important here at all. No, this is the very start of the dynamo. This is going from your weak C field. You know, if you make that C field equipartition, you just land straight into the saturated state, straight into this stuff.
So I think the answer is yes. You assume the very weak.
Bmag, much less. Wait. No. I'm thinking of like a primordial magnetic field and then it evolving over cosmological time, or I'm thinking about just I'm thinking about a very weak magnetic field stuff, and one that doesn't fill all the K space. I want it to naturally evolve through K space as it wants to. And we call this the diffusion free regime because the magnetic field feels no resistivity all the way through this entire regime until it gets to the resistive scale. You know, it's existing on relatively large scales compared to the resistivity to begin with. So this is like the onset of a chaotic magnetic field, in other words. You know, it doesn't have any high K mode structure, it's quite a uniform boring magnetic field. It gets hit by the turbulence and gets turned into the field that is exponentially growing in every way it can. So many exponential processes here. It really is the maximum, like the fastest that you can grow a magnetic field in this regime.
Has anybody separated into K perp and K parallel?
What does that mean?
It means that, it's probably wrong, but the vision, given that it's stretching, is that it's stretching out.
Yeah.
field, But.
Yeah, so
that
these,
cross field lines and, you might get a different story.
so these gammas come from eigenvalues of the velocity gradient tensor. And the eigenvalues of the velocity gradient tensor tell you essentially how a fluid element is stretched in a volume preserving way. Right? So the eigenvalue associated with this is the 1, 2, and then there's a third eigenvalue here. So let's say that we have a magnetic field from here, and you stretch the fluid element, that will actually give you exponential growth associated with this eigenvalue. This eigenvalue ends up coming into the equation. One of these versions. So this is about stretching along the magnetic field. There is a directionality to it. You can actually do some really nice calculations to work out based on these eigenvalues about why magnetic field growth for a small scale turbulent dynamo is possible in the first place. You know, what modes will grow, what modes will decay, etc.
Yeah, it's just. Maybe us. Off topic, but it's got some similarity to basements and when you create gravitational systems where if you just look at with a bit of course raining, you can see it as heat. But if you go right down to it, you can continue with this kind of phase sheet.
I see.
Differences
Sounds
are
good.
stress, so. Right.
So let's just talk about the next stage because this is an interesting stage as well. Essentially, the power spectrum and the structure that you develop. I feel like I have my back to this part of the room for ages. The power spectrum that you develop during this first diffusion-free regime, where the magnetic field is just populating every K mode all the way down to the small scale as possible, stops as soon as you get to the resistor scale. And then there is just self-similar growth in the entire magnetic field. And by the way, the scales here are terrible. You know, the kinetic energy should be way larger, it should have much more energy. But now we get into the diffusion regime, where the magnetic field knows about the resistivity very well, and every single mode grows with the same rate exponentially up, just straight up. So the whole spectrum is maintained in the same place, in the same structure and K space, and just grows straight up. Now, there's number 3 is the nonlinear stage. So if you remember, when I wrote down the momentum equation, I had this term. Which was the magnetic tension. And we had the quadratic nonlinearity that we love so much. So that momentum equation for the first part of this entire process looked fundamentally hydrodynamical. And the reason was, of course, the magnetic energy density was very low at the start, very low. So all of the magnetic terms, the momentum equations, like G squared. So the Lorentz force, the Maxwell stress, it's all very small. But it's growing with time exponentially. And what happens is that you get to a point where the magnetic tension and the Reynolds stress are of comparable order of magnitude, comparable size. Now, the induction equation, which looks, when written out like this, looks completely linear in B, right? It's completely linear in B. But now U depends upon B. It didn't previously because the Lorentz force was so weak. Now the magnetic field is coming into solutions for U, and this whole set of equations becomes strongly nonlinear as well. So one can actually get from 2 other arguments that from that kind of process, you do get that the magnetic field grows linearly. And the actual proportionality factor to order unity is the rate from this NV flux, the constant NV flux. So this is very neat, but people haven't tested this properly because the nonlinear stage is quite hard to measure in simulations. Because what is also happening in the nonlinear stage is the whole spectrum is actually rearranging itself. It's actually coming back until it gets back to something that looks like the kinetic energy spectrum. So it undergoes this huge rearrangement as the peak scale moves all the way back up close to the outer scale of turbulence. And as it's doing this rearrangement, it's growing secularly in time. So I think that's all we have time for, and I've already gone over time. Of course, saturation, there are lots of interesting physics, like why does the magnetic field saturate particular values it does, what sets the saturation, this stuff is still unknown. People think it's a mixture of the resistivity grows. You can see that when the, if we're in a steady state, so in saturation, you essentially get a balance between these terms. Well, this is just the advection, so we can get rid of that. Balance between this term and this term. So what's happening is it this term that's growing, or is it this term that's shrinking, or are these two kind of things related? What's the physical process of saturation? So this is still unknown. The saturation is still unknown. Chris.
So what is the logarithm rate of K max?
Yes.
Decrease?
Yes. It's
Compared with the hydrodynamic.
it's like log PM 1/2.
So it's a logarithm to the.
Yeah.
So you're talking realistically about.
Yeah. Yeah.
So this then gives a order of magnitude estimate. The level of which is secular. Secular. Part of the stress, which doesn't fluctuate, it's not. That is.
Yeah.
This year, whatever. You can see that. If it's smaller than 1/over the logarithm,
Yeah. I see what you mean.
then it's gonna get lost in the common narrative.
I do want to say,
Larger.
I want to err on the side of caution here because, like I said, I would say like we understand these regimes very well and we can probe them numerically really, really accurately, which we've done.
But less attention given to the slides.
Less attention, but not only that, because we are limited to relatively small PM in our simulations, because we need to essentially have all of these K modes in our simulation so we can resolve the magnetic field moving to the smallest scale as possible. And then we want to see it move all the way back. And if this PM is very small, that's very short. And you can't even work out the time scales properly for the process. So what I was just saying, like log PM to the 1/2, that hasn't even been confirmed numerically. Yeah, but the theory says it should be log.
So what PM is becoming feasible?
Well, here's the other thing. I mean, when you go to high PM, what are you going to sacrifice? You want to sacrifice your total spectrum, right? So you go to low RE. And then when you go to low RE, suddenly the saturation changes. Yeah.
Let's say you have RE of 1,000.
RE of 1,000,
What PMs?
I would say.
All the GPUs you can possibly throw at it.
I would say PM 10,000 these days would be possible.
Maybe just the fact of 10. Well, PM of 10, yes. So hang on, I wasn't the 10 second.
Wait, no, 1,000. 10 to 6, 10 to 10. And that would be doing 10,000 people blocks as well. That would be pretty crazy.
So, can I just ask you about the K-space structure here? So the grad U term, which is the shear, that must not have any power beyond the dissipative scale.
Yes, that's
And
right.
so somehow.
It just gets washed out after this phase.
Well, then why is that giving such a dramatic effect if that's supposed to work?
Because of how.
At very high K.
Yes.
Interacting with something that's at rope.
Yes, but it's because of this. It is where the gradients are being washed out.
Just say what that is.
Oh, so it's a ratio between time scales, right? It's because the smallest eddies. So how I want to plot this T as a function of L. No, this is like L 2/3. The smallest eddies have the fastest time scale. So even though the gradients are getting washed out on these scales, they are evolving really quickly compared to the lower K modes.
But that's affecting these at extremely high K.
Yep. When you do the transfer functions, and this is working out how the energy is flowing through the system, you find non-local, it's all non-local. And the engine, like I said, is all coming from K nu. It's like this.
Yeah.
That's how the energy is getting. It's amazing. Like it's been, and this should worry people in global simulations because this dynamo, I mean, you have to think about resistive scales and viscous scales. And you can work out through tilde arguments, of course, that essentially during both these phases, that the magnetic energy, Emag, t is going to scale like the exponential r and re to the 1/2. So this should worry people as well, because people in, most ILES people, most people who don't care about viscosity resistivity will never even have a handle on how fast their turbulent modes should be growing, their magnetic modes should be growing. So this has always worried me about global simulations. So they really underestimate the effects of the small scale dynamo. One, because their Reynolds numbers are very small to begin with, even if you don't have any explicit viscosity. But two, because the dynamo is very sensitive to the magnetic random number. You can imagine this whole, this whole growth stage really is much, much longer if you have to go through all of these K modes here. So the actual growth in Emag, it shoots up for much longer if you go to higher PM in this diffusion-free regime. Then it goes kinematic, then it goes nonlinear, then it goes separate. So you can get a lot of growth in the very early stages of the dynamo if you're in a high PM plasma. And people just do not capture that in simulations.
Even cases like very dynamic cases of port clouds, where you have this big convection outside this cloud star. So as resolution so much is increased, but then we have a field, so seeing all sorts of information that this wasn't a bit
Yeah,
realize it.
I mean, the literature is definitely, a lot more people think about PM these days, I would say, by.
Modest time. But like
Plasma people, so.
So, is it possible to forget about the dynamo part, not the dynamo part, the cascade part, and just try and model the thermal velocity, the thermal shears, and then you just have that driving?
Yep. So that is how you get to the magnetic spectrum in the first place.
Oh, you mean you don't do a complete calculation, you just drive it by a.
Well,
short distance structure?
we essentially, we pick a correlation function for the velocity. That is delta in time. And then the correlation can, then just some.
Yeah, okay. I'm just bringing this up because sensitivity would mean that the specific form it is or evidence, it could be sensitive. It's kind of a mediation.
Sensitive to what?
If the region of heating is the finite width of K, which it should be, then it would be a different driver.
I don't think, that, sure. Yeah, maybe it's all about, can you suppress the scale? It's all about when you drive with the scale that has the shortest turnover time and has some velocity gradients.
Yeah.
So I don't think it changes the picture.
Well,
Right.
That's not clear.
Okay. Well, let's leave it there because we're going way over time.